presentation this evening will be a CO2 information session, understanding the labyrinth of zero emissions and engineer's perspective. Our presenter will be Jacob Cherian. Jacob has a BSME from the Indian Institute of Technology, Kanpur, and an MSME from Iowa State University. He currently holds the position of mechanical engineer working for ACT Talent in the automotive industry, where he is recognized for strong analytical abilities. He started his career in concept models at EASI Engineering before moving to NVAH CAE at Ford Motor Company, where he held assignments in body design release, value engineering, launch, assembly plant variability reduction, and analytical simulation efficiency. His experience spans large organizations interfacing with company experts to drive technical solutions with problem solving, training in Lean Six Sigma, Carnegie Way, and Sharon Red X. Using his experience gained in the industrial environment, Jacob has gone outside the primary technical path to research the subject topic and put it into a sensible language, giving a better understanding of CO2's role in the environment without the negative hype. Today's presentation will cover climate change using the insights of industrial problem solving, summarizing the labyrinth of legislative research and judicial history driving zero emissions, court decisions, vehicle emissions ruling history, EU history, and EU carbon tax history, and looking at the KEELING curve and showing the influence of heat islands and the complexities of a spinning Earth. Okay, Jacob, that's a lot of stuff. Take it away.
All right. Thank you, Chuck. Thank you for that nice introduction. And thank you for inviting me over here. This is a material I've actually compiled for a couple of years now, and looking for forums to share. Part of it is for both education for everyone. I'd love for kids to know about this. I work with middle school science Olympiad groups, and I would love to get this kind of technical information to our youngsters, right? Our youngsters have the future Zuckerbergs out there, and so I want to make sure that they understand some of these complexities, right? So there is intricacies over here. I have about 25 slides over here. I'd love to go through it all and then open it up for questions, right? And same goes for people online as well, right? So thank you for joining the session. With that, let me get started. And so let me start with this slide over here, right? So I do have, as Chuck mentioned, I have both an engineering background, and plus I worked in the assembly plant for a couple of years, right? So one of my assignments was that. And on the assembly plant is a particular kind of situation, right? You have a normal, and then something goes out of normal, and you have to very quickly solve it, right? And you're working with a large group of people. There's a lot of pressure there, but there are certain disciplines which have been built around that system, right? So some of the problem solving goes through that. What I'll focus on over here, the first part of my presentation, is this question here: what the problem is, right? So, in the structured problem solving approach, we try to break it down into matrix items that we can measure, and it's like a y equal to mx type. You're trying to figure out what your causal factors are, what's causing the issue. You try to take data, sort of the Six Sigma approach is like, can you measure it? How accurately can you measure it? Are you measuring it, if you measure between different operators, or if you, between shift, you get the same measurement? What's your spread in data, that kind of issue. So there is a part of problem solving looking at why, but this is the basics of it, right? An effect and cause. As you get deeper into this, the science of it, just problem solving, there is this matrix on the bottom right corner, the decision matrix that you go into. And so with any hypothesis testing, you do have what's called your alpha beta risks, right? Your errors. And so, you have the real world out there, you have your model, your hypotheses, and essentially you're trying to minimize the type 1, type 2 errors, right? So they're in the most models will have some kind of a type 1, type 2 error. You're trying to minimize that, right? And you make your model. There's always a room for continuous improvement in that segment too, right? But that would be the heart of any like science-based methods, right? You do go through this. You do go through you formulate a hypothesis, you test it out, right? In the problem-solving approach in the industry over here, I've gone through Global 80, Kepner-Trigo. Again, they start with, there is a step to define this, the problem, what the problem is, right? A method, what, where, when, how many, and then it is trying to break it down into what is the measurement that you should be measuring, right? That's kind of the heart of it, right? So with that, let me get into the meat of the problem over here. So these are both, I think, widely seen curves. The graph on the top would be your temperature over the surface of the Earth. That and the bottom, the graph on the bottom is the CO2 measurement, right, at one location. The graph on the top, this particular one, there's actually a few different variations of that. This is one particular one that I like. I happen to trust the data, but if you look at this data, the vertical axis is in terms of temperature, like the smallest box is 0.2 degrees Celsius. The horizontal scale is the number of years. And this is data taken, it's average temperature over the surface of the Earth, right? So the Earth is a spinning object, but this data is taken, people calculate it, and it is published, right? So there's a few different variables of that. The graph on the bottom is, that is the Keeling curve. Again, this particular one is hourly measurement at one location, and you do have one trend coming out, right? So question I would pose over here is, which of these is the least confounding, right? Which, so going back to the Keeler curve, so the challenge I had over here, right, is trying to understand why are we not just simply using the Keeler curve, right? So in terms of problem solving, that seems to be the more robust type measurement, right? So there is I mentioned I've spent about a couple of years looking through this, and this is some of the labyrinth of the problem right over here. So what happens is there is this number of legislation type issues going on. There's but let me explain that some of the science over here, and just going through the boxes over here. You have the calendars research, and there's some prior work before that also, trying to link carbon dioxide and global temperatures. There is, and then that bottom, that on the top, that goes to there's a link over here, 1957, then 1958 is Charles Keeling, that particular measurement, right? On the left side, there's another trend, parallel trend over here, which is interesting. 1940, Martin Kamen is actually trying to study photosynthesis. He's looking for a stable isotope. He discovers C14, right? He ends up missing the Nobel Prize because his co-author perishes in a lab accident, right? And so they couldn't actually, it's a joint venture there. That work is used in Melvin Calvin's work, that's 1961. The 1957 work actually picks up on Kamen's discovery of C14 and uses it for some other purpose, right? So C14 discovery is a huge issue, right? It's used for carbon dating. It's a lot of other aspects to it, but that's, so Roger Reveal's work is actually interestingly tied to the C14 discovery, right? There is now what are the other aspects of this? So there is 2007 there's a Supreme Court ruling, right? And I'll talk about that a little bit more in detail. But part of the background to that is that you should know about is there's an EPA. The US has a particular stream of how rules and regulations are set up. The US had the EPA. The US had the Clean Air Act there, and then the EPA was founded. EPA has certain authorizations. They were authorized by Congress to regulate industries, right? Regulate pollution. That work is foundational to the U.S. Systems, and then U.S. also has the corporate fuel economy. That system set up as in the wake of the oil embargo. Right? The parallel system in Europe has a different history, right? So Europe, and I'll go through that also. But the European setup has been a little different. They don't have a regulatory body like the EPA. They have their enforcement. It's more of tax directives that they have, right? So we'll go into that a little bit, but some of the history of that. This is this is some of the background I'll go into. So it's the labyrinth of change over here, right? Now back to just plain science, right? The plain y equal to mx type equation. So what is the relationship between graph A and graph B? There's a lot of literature published on this. Part of my goal from this presentation was this to be readable by high school students. I would point to this particular paper over here. This is a 2021 science paper. It's about 12 pages long, but it's a good summary of the relationship between graph A, graph B, right? What is that? How it's linked, right? And that's the again, this is I would say that's those. If you think in terms of hypotheses, yeah, that's a hypothesis there, right? But this is, you have to establish your relationship there, right, between the two. I mentioned there's a lot of literature out there. The IPCC is, you have gone through several stages of publication. And IPCC, you do need to understand this particular term called radiative forcing. I've put a quick summary of it over here. Radiative forcing. Again, let me put it this way. Like in my work I work in my engineering career here. I work with the simulation models, and in VHC simulation models, and we try and correlate our models to physics, to what we test. And we have to use simplifications at times, right? So the most common example is where you're taking, is it a simply supported beam, or is it like a clamped condition, right? The clamp, because that will affect the amount of deflection, right? So most times we would try to simplify to, hey, can I fit either of these extremes, right? Because if I can fit into an extreme, it's much easier to calculate, right? So you have to keep in mind those kind of simplifications that go on. The idea of radiative forcing is a particular simplification used over here for the climate models. Just be aware of that, right? That is one approach used there, right? And I put a link over there to IPCC has a lot of material online. Now, another part of this labyrinth, right? And I think there are several labyrinths to understand, right? So one of the labyrinths is what I would call, this is the litigation side of it, right? So the US has a judicial branch, and judicial branch, again, the people going into it who would enter into this stream, they have to go through law school. It's a fairly challenging, demanding credentials. So it draws a good stream of people, and the top of that expertise ends up being in the Supreme Court, right? So they're the best of the best over there, right? So in the Supreme Court, so again, the Supreme Court authors there's cases presented to them. They would make a decision, and it's like in the US we have, so this is a 5-4 decision there, but the Supreme Court authors do write an opinion, right? So and in cases they can write a dissent, like the majority. Usually there's at least one dissent written, the majority writer. In this case, there's another dissent written too, in case of the 2007 ruling, right? The 2007 case is kind of interesting. It started back in 99. There was a group which filed EPA to start regulating greenhouse gases. 2003, EPA came back and said, no, this doesn't fit our charter. It went to the district court in 2005. Again, that was there was a decision made. It ruled in favor of EPA. I think it is those decisions are online, and again, you can read with the Supreme Court, with all these court case decisions. You can read both the opinions, the dissents, and it's good information out there. Good learning over here. With Supreme Court decisions, again, these they set precedents, right? So you're making a judgment, as well as it's a precedent for future cases too, right? So that's part of the maybe part of the reason they write their opinions out there. But the meaning of the 2007 ruling, I started looking into it because about 2 years ago, there were some opinions out there saying that Supreme Court has ruled that carbon dioxide is a pollutant, and I was actually interested in the threshold. Was that what was investigated? Did they establish a threshold as to a parts per million ratio? Is that what was present? And it turns out, no, that was not what the arguments in the Supreme Court were. There's a law paper out there which, again, this is all legal. It's a legal labyrinth, and in the legal term, this is more about it remanded the case back to EPA to reconsider its decision. Right? It's probably a better technical reading of the issue than. So I put this down again. I believe these are. So I have a PDF of this presentation. I'd be happy to share. There are links over here that you can click on and get further information. Right. So this is more about helping to sharing information. Right. I found it useful. Again, this one is a link to a legal paper. Right? This issue came back to the Supreme Court in 2021. Supreme Court, it was West Virginia versus EPA, plus some other cases lumped together in that. That ruling was made last year. Again, that was against EPA, but that you can read the opinions, the data. This is a 6-3 decision over here. So that's part of the legal framework. Now, the 2007 ruling, especially in the Supreme Court ruling, had to do with vehicle emissions, right? The subject matter being discussed there, the topic was new vehicle emissions. Right? So, new vehicle emissions, the how regulations happens is a complex matter again, right? So you're taking science, but you're also going into the lawmaking bodies to make legislation, right? So the U.S. has a particular history on legislation. It turns out there's a good paper out there. This is good committee report, actually. The report was commissioned in the wake of the Volkswagen emission scandal. So the European Parliament had commissioned a report, and that report actually has some very good history about how the US set up their rules and the European Union set up their rules. Right? Great history over there. So again, for students high school, I would strongly encourage a reading like this. Right? It's good material to go through. Good to understand what the legislative framework is in Europe and the US. Right? So it's different systems there. Right? So again, I've summarized over here. The US is energy-based. The EU has it's a little different framework there. Let me talk about that. Let me talk about the European history to put a little bit of context over here. European history itself starts more in the wake of World War II. After World War II, World War I actually had been prolonged because of the coal and steel. Coal and steel are used to for war making, and with war, once you start it, it's very difficult to stop, right? So, but it fueled that industry. So especially between France and Germany, that steel and coal had a lot to do with the prolonged nature of the conflict, right? So 1952, those two they come together. They say, okay, we're going to try and prevent this, and so that was maybe the history of the EU starting up. By 1993, the European Union is created. Again, European Union is for free movement of people, goods, services. So rulemaking in the European Union happens to be different here, right? So EPA has authority to impose fines, to make measurements, impose fines. European Union has a different process that they follow, right? So they have a governing body. They would meet, discuss taxes, and that's part of their legislative approach. Right? There's also a history of carbon tax in Europe, right? So carbon, again, certain countries had implemented, like Sweden implemented the carbon tax. The reasons for the carbon tax, again, it's borderline between energy and pollution, right? So it's somewhat, it can be a revenue generating source as well as going to going away from the carbon based fuels, right, and going to a different system. Again, keep in mind that this system, the carbon tax, is about economics, right? So these are economic experts who established this, right? And again, that's an entirely different branch that you need to be aware of, right? So there's expertise in that which went to regulating this, right? So it's a different branch over there, but that's another labyrinth to be aware of. Okay, now let me go back to areas I'm familiar with. So let's just talk about the Keeling curve, right? The Keeling curve itself. The Keeling curve is data that Charles Keeling is. I think he was a graduate student, but he ended up creating a device to measure CO2, right? And so he comes up with a very sensitive instrument, and it's a unique instrument, but he gets funding to be able to take measurements. He sets up this apparatus, and his data ends up is this the curve that we see over here. And I'll go to this from a metrology, that's a measurement point of view. This data is fascinating, right? So the data, if I expand the data and I just look at the annual swings, right? You're seeing a very periodic pattern over here, right? And it's repeated. I see the amplitude doesn't change. If you look at the numbers, they're actually decreasing, right? So there's a period where it goes up, but then it comes down, right? And so it's a very interesting phenomenon. Now, I've worked in the manufacturing world. We had to look through like warranty data, for instance, right? And we're looking through data. If you're responsible for your system, you're supposed to be able to explain to the management team why you're seeing an inflection point in your data, right? So so there are the inflection point is both the going up and the going down, right? So there are a number of inflection points over here. We would have to explain it, right? What's causing these inflection points, right? So it's an interesting spread of data. Again, this is all published online, easily available. Again, there's a little spread in the data in terms of the daily, weekly data. There's a spread, but when it comes down to the monthly mean, you're seeing a very, very nice pattern. Right? So I would say there's something to be looked at. One of the questions I ask over here is this is cause or effect, right? And in a nutshell, that's the question you have to ask over here, right? Is this the X variable or the Y variable, right? Which one would you consider this for the problem at hand? So just mapping this data to phenomena, I know that weather is caused by the Earth's axis tilt. The tilt ends up causing weather. Is the tilt also, are we seeing a swing because of is there a heating cooling of the oceans going on, right? Is that what's causing is that what's causing that periodic swing, right? And I say this because again, it's a very constant amplitude type phenomena. It hasn't changed for the since Charles Keeling started taking that measurement. We're still seeing that same up and down pattern. What's constant? I mean, the ocean is a very large body of water, so perhaps that may be why that may be more a cause over here, right? That's causing this constant up down type pattern. It's an area to look at. Another aspect we get into on the shop floor when you're trying to solve a problem is trying to identify items which are out of control. So what is the threshold, right? So what is the parts per million level where you know something is out of control? Again, going back to the EPA founding, right? When EPA was founded in 1970 and again 1977, when they improved their techniques, they had actually set up pollution levels, right? This is good, this is bad, right? So those levels were established for the pollutants such as lead, which is harmful to health, and we actually enjoy the benefits of that, right? From those regulations which were set up, you actually trace to fairly clean. I mean, we breathe clean air over here. Like Detroit has got very good air over here, and it's different than maybe other countries. Many other places. Even I've grown up in India, and there's a different level of pollution. Let's say Bombay, for instance, a different level of pollution. So, but we have the benefit of Clean Air Act, the EPA. Part of that is getting threshold, right? So this for CO2, what is the threshold? I started looking into it. Carbon dioxide is used during photosynthesis. It is an endothermic reaction, but that means it absorbs energy. You have, I mean, it is cooler under the trees, and so there is a heat absorption going on over here as well. In terms of parts per million level, right? These are two graphs over here. Greenhouses, where our ambient level is around, it's about 400 now, but plants grow at an elevated ppm level, right? So they can go up to like 1500 ppm, and they're safe, right? For the toxic, it becomes toxic after, like, say 2000 ppm. For humans, it's more like 5000 ppm that it will become toxic, right? So, so the toxicity for, again, humans, it's studied a lot in like pilots or submarines, or there's data out there. So it is, after a certain level, it becomes toxic. After about 5000 is where you'd have issues for, I believe, in a it's more regulated at that level, right? On the right side, I have this combustion efficiency chart. Combustion does produce CO2. You're looking at burning. You're looking at trying to burn the fuel completely, and so the engine cycles, the optimal, efficient engine, or even your high efficiency furnace at home, high water heater. Those all are trying to make effective use of the fuel, The fuel would produce CO2. That CO2 in a combustion cycle, say somewhere around 10%. That's in terms of parts per million, that's several orders of magnitude higher than what we're talking of over here. So, but again, this is just reference information, good for everyone to be aware of. I'm looking for what is the ppm which separates the two ones. Right? Some other aspects to be aware of. Heat islands. Again, this is there is a phenomena out there called heat islands. If you remember the graph some pages back, we were talking of like 0.2 degrees Celsius. That's about the level of global climate change. In terms of what we're talking of heat islands, these are much bigger deltas, right? So you're looking at almost like 22 degrees between night and day. Temperatures. So there is there's a heat effect of urbanization, and it's again nature. Concrete it will end up being much more warmer. It retains the heat longer. If you have been in rural areas, you'd have experienced this, right? So, let me show this other picture over here. This is what we Red Rabbit is in the industrial problem solving. If you have set up controls, you test it, right? You have to test it, make sure your controls are able to catch the defect, right? So one of the it's just testing your theories, you're testing your hypothesis. So what happens if I do an empty parking lot, right? So right now, a lot of our efforts are focused on controlling greenhouse gases, right? That's been I guess the vocal information out there is controlling greenhouse gas, right? But what happens? What about the empty parking lot? It's the empty parking lot. Right now, with the greenhouse model, you're strictly just looking at how much gas emissions it's putting out, right? So, and it ends up being minimal, right? There's not much greenhouse emissions there. However, a parking lot is taking away from vegetation, so you have lost the capacity to absorb solar energy. There's an Earth's moisture cycle. You're blocking that. And then there's this other item over here. When it rains and you have a very hot parking lot, that water gets heated, right? I mean, the rain cools down things, but the water will get heated up. And so because the water gets heated up, it can be it flows into the streams. The streams, it's bad for aquatic life. But again, these, if you have a lot of this going on, does that affect the, perhaps even the oceans, right? Are you with all the urbanization that we have, does it end up be putting warmer water into the oceans, right? So that's again something to be looked into. I think of with a large problem, you may have multiple causes, and you have to nail down all of these, right? NVH in particular, I see Pranav is speaking next month, but NVH in particular, you have a number of issues that you have to address, right? And then you start bringing the levels down. So great challenge. So here you have large factories, building complexes, even a multi-acre greenhouse. So that also captures your hydrological cycle, right? So you need good regulations, right, for all of these. This again, I would offer this more as a research type area, but I bring it up here because I didn't see it mentioned, but in some other presentation, it's covered in my next slide. But the Earth's weather, as we know, it is significantly influenced by atmosphere and ocean currents, right? You have the jet streams which drive like our polar vortexes. We get very cold days sometimes. That's the jet streams. There's the ocean currents too, which have a a dominant effect on weather. So if I look at the weather in Florida versus the weather in California, California gets pretty dry, in summer months, right? You don't have greenery there. You have more yellowing grass. Florida gets a lot of water, right? A lot of moisture. A lot of it has to do with this, the ocean currents, right? So the ocean currents do play a significant role in like the local weather. Right? So we know that. I mentioned over here hurricanes. Hurricanes are known to form. This is actually from middle school science Olympiad, but we know hurricanes form when there are certain conditions, and one of the conditions is that the water needs to be at a certain temperature or a certain depth. Right, once it reaches that, that's a recipe for hurricanes. Right, this kind of, again, hurricane is a large, it's extremely large heat engine. Right, it's generating that, but part of it is you're getting warm. You need warm water. And if I look through, this is the part I didn't see enough research out there when I do search. I think maybe a good item to understand. But we know there is, I mean, you have the floating plastics that's well addressed in the media. But there's another item called the microplastics, right? The microplastics ends up being a lot more magnitude of microplastics is there than what you see floating in the ocean. Again, some of the microplastics would float down. They don't float at the surface; they would go down. But there is microplastics which float at the in that upper part of the ocean. In the ocean, again, you have if it's this area above the thermocline, if that gets heated up, that can cause adverse weather. Is that happening with the microplastics? Right. Again, I think this is a research area. I would love to see more work on that. That's one area to go into. Right. Then let me talk about the solubility over temperature. Right. Gases are gases are soluble in liquids. There's certain laws governing that. They happen to be less soluble at higher temperatures, right? So if I think of the beverage can, your beer cans or any carbonated drinks, those are in manufacturing, they would be bottled up. They'd be first chilled out. The beverage is first chilled, and then then it is carbonated, because the colder the material, the more it can absorb carbon dioxide. Right? So it's part of the manufacturing. I mean, it's part of how carbonated drinks are made, and we know this, right? So the question I have is, could the Keeling curve actually be the better? Could it be just showing you the temperature, right? So can it just be showing the warmer temperature? Again, what happened? Let me go back to my slide over here, and I'll open up for questions. But over here, what happened is in this 57 paper by Roger Reveal, that actually looks at the carbon dioxide from industrial, all the carbon that we are burning from fuel. And he makes the argument that there's too much of it burning, the oceans can't absorb it, right? That's just his argument. He's actually using measurements from Martin Kamen's discovery, right? If you look at the dates over here, there is a 61 is when Kelvin publishes his Nobel Prize. By the way, Kelvin was the first chemistry graduate from Michigan Tech, right? So it's an interesting reference over here. But his paper, again, is fascinating research, but it it's like a Nobel Prize level research. That has to do with carbon estimation into plants, right? So I'm kind of curious if the data that Roger Reveal was looking at, is it tied in? Like, are these two parts of research tied? If they were, would you see a different conclusion? Right?